Let's start with vanilla convolutional neural networks. Vanilla convolutional neural networks go back to about the late 1970s, but they were really popularized during the 90s by people like Yann LeCun and colleagues. But it was only really in about 2012 when they really took off with the success of AlexNet, courtesy of Geoffrey Hinton and colleagues. But this is not a talk about convolutional neural networks, which is a very broad topic in its own right, because there are many ingredients in a CNN. So you need things like the readout phase, there's dropout regularization, there's the non-linearities involved, and of course the convolution, which is the defining ingredient. No, this talk is just about convolutions themselves, which might sound very niche, and that's because it is. But it will turn out that convolutions are actually a very rich topic, and if we really want to understand how to learn the patterns in physical fields that are of interest in physics and chemistry, then we really need to get to grips with how to do convolutions on objects that are more complicated than just images. So I'll describe that throughout this talk, and I hope it's enlightening. The notation I'm going to use is I'm going to use V to denote the physical field generally speaking, or in this case for now V will just denote the image. I'm going to use F to refer to the kernels. I'm using F because kernels are sometimes called filters. Kernels and filters, they're just synonyms. And I'm using L to refer to the feature map. I'm using L, V and F because this is the notation used in equation 3 of the tensor field networks paper, which is basically what this talk is really all about trying to understand. So by using a consistent notation from this starting point all the way through the entire talk, I hope that the pathway to understanding the equivariant convolutions shown in the tensor field networks paper is a bit easier. So what actually is a convolution? Well, it's just an array of numbers being multiplied by another array of numbers. The simple technique is just to take the convolutional kernel, an array of numbers, line it up with the image, and then you just multiply the numbers that are next to each other. Doing that multiplication gives you another array of numbers, and then in a CNN you just take the sum of that array, and that sum is then the new value of the corresponding pixel in the feature map. I emphasize that we choose to do a sum because a convolutional network, or a convolution I should say in this particular context, is really a special case of a much more general approach called graph neural networks or graph convolutions. And so we don't have to do a sum. We could do a maximum, or we could do some other aggregation rule, generally speaking, although in the context of CNNs we'll just be doing a sum. Probably one of the most important concepts to understand at this point is the receptive field. So the proportion of the image that the kernel overlaps with is called the receptive field. In this case it's just 9 pixels, and that's important because what a convolution is really all about is not just saying what's going on at a point X in an image. It's about saying what's going on at point X and around the neighborhood of point X. And by taking all of that information about the neighborhood around a point and condensing it down to a single point in the feature map, we're actually collecting lots of information about what's going on in the neighborhood. And so what that feature map is really about is a summary of what's going on at every point and its own neighborhood. That will become perhaps a bit more sort of intuitive in the context of, for example, molecules, because let's say if you want to do a convolution on a molecule and you're doing a convolution at a particular atom, you might want to take into account what the surrounding atoms are doing and how they contribute to that feature map. So that's why the receptive field is a particularly important concept. So just some mathematical pedantry then. These functions at the moment, VF and L, they're just maps really. So we're mapping from z squared to the reals in each case, and that just means you specify a pair of indices that tells you which pixel you're looking at along the x and y directions, and then for that pixel you just have a particular pixel value, a particular intensity. They might ask, why are we not mapping z squared to z? In other words, for example, an 8-bit grayscale image, the pixel value is just an integer between 0 and 255. Well, that's true, but in a typical machine learning pipeline, those values will be compressed down to the range 0 to 1, or maybe to the range -1 to +1, depending on the architecture and depending on the application. So really we're mapping ordered pairs of indices to floats. One other device that we need is the translation operator. And that's really just because we need to be able to scan the kernel across the image. In other words, we need to be able to translate it. So we'll define a pair of indices A and B, and then we'll define the translation T sub G, where the translation of the kernel happens by an amount A and B, which is, like I say, it's mathematical pedantry, but it's necessary to write it all down for completeness. So let's take a look at an actual convolution happening. Notice that the U and the V indices, they move with the kernel. U and V tell you where you are in the kernel, and the indices I and J tell you where you are in the image and in the feature map. So I'm using I and J as the coordinates for both the image and the feature map. It just makes everything a lot simpler. And the kernel has its own coordinate system. So the indices U and V move with the kernel, and that's really the way to think about it going forward. So we can take this position in which it's currently situated here and actually work out how we calculate the value of that pixel in the feature map. Well, like I just explained, you just multiply the pixels that are next to each other. So here we're just going to multiply V by F. Now the indices 2 and 4 in subscript on the V, they just correspond to the fact that we're at position IJ in the feature map and in the image. And then that offset, U and V, that just tells you where to go in the kernel in order to access all of those pixels in the kernel, so that we can multiply all those pixels in the kernel by the corresponding pixels in the image. So it's one of those equations that you just sort of look at for a few seconds and then it makes sense, I hope. So if we want to describe every pixel in the feature map, we need to describe L subscript ij to refer to the ijth pixel. And again, it's really just a generalization of what I just described. So we specify I and J, which tell you where you are in the feature map, and then U and V, which tells you the kernel offset required to access all of those pixels in the kernel, to multiply the kernel by the image to give you the feature map. In this particular definition, I'm using a kernel-centered definition, so the values of U and V go in the positive and negative directions, although you don't have to, but I like it this way because I just think the algebra is a lot more simple. And another perspective from which to look at this is to consider the image and the kernel as scalar fields, because they are, because the pixel values are just scalar values. We're not dealing with vectors or tensors yet, although that will come later. So from the point of view of like the physics perspective on what a convolution really is, it's basically a point-wise tensor product of spin zero discrete fields. By discrete, I just mean we have discrete pixels. By spin zero, I mean that they're scalars, and why it is that they're spin zero will become clear a bit later on as I explain the concept of spin in the SO2 case, which is what really this talk is mainly about. So if you don't understand that physics language at this point, don't worry, it will become clear a bit later on. Now, in order for convolutions to be useful in physics, we need to make sure that we can actually bake in some physical symmetries. One of the most simple transformations that you can do in physics is to just move something from here to here, which means translating it. So let's say I have an image here. I'm going to take the 7 from MNIST. And if I translate it down and then do a convolution, the question is, do I get the same thing as if I first do the convolution and then translate it down in the feature map plane? Now I've noticed here I'm using G to refer to the translation, whereas on a previous slide I used G to refer to the pair of indices that defines the translation. So perhaps I should have used T sub G here, but if you'll bear with me, I'm using lowercase g as a group element of the translation group to represent the translation. So the answer to the question is yes, we do get the same thing if we do a translation and then a convolution as if we do the convolution first and then the translation. That's because convolutions are translationally equivariant. What equivariance really means in this context is that if we do the translation in the image plane and then do the convolution, there exists a simple, predictable, deterministic relationship that relates those two feature maps. And in this case, it is just another translation in the feature map plane. That's a really important concept that will come up again with more physically interesting and relevant transformations, things like rotations in 3 dimensions, for example, which we'll get onto. But for now, let's just go ahead and actually prove that convolutions are translationally equivariant. So we'll use the convolution definition that we just derived. And I warn you, this proof is a bit underwhelming, but it's necessary to write it down just for completeness, and it's quite instructive, I suppose. Okay, so just like we discussed then, let's do the translation first, g of v, and then do the convolution. Well, translating v just means that we can modify the indices accordingly, so we just subtract a and b from the indices I plus u and j plus v, which is, like I said, a bit underwhelming, but that's what you get. So now if you do the convolution first and then translate the result in the feature map plane, well, we can write that down by just adding u and v, by subtracting a and b respectively from I and j. And so purely by associativity of addition, it's pretty straightforward to see that they are both basically the same. And that is a rather underwhelming proof of translational equivariance in the discrete case for convolutions. Now let's move on to continuous fields. So it's really much the same. We're still dealing with scalar fields with spin 0. We're still doing the convolution in very much the same way, except now, rather than taking arrays of numbers and multiplying the numbers that are next to each other, we're just going to be multiplying functions together. So rather than dealing with sums, we're going to be dealing with integrals. And we can define our images, again, just as simple maps from r squared to the reals, meaning rather than specifying a pair of indices to say which pixel you're on, we now just specify a pair of coordinates which tells you where you are in each one of those images. And in a similar way, we can also define a continuous translation operator that we need to scan our kernel continuously across the image in order to do the convolution. So just like before, we can write down the expression for the convolution in the continuous case. It is possible to derive it using a continuous function defined on a grid, and then you do Riemann sums and make identifications of them being equivalent and so on. I think life's too short for that sort of derivation. Honestly, this is just one of those things that you can write down, and it's just really intuitive and kind of obvious. So the only changes in notation that are important here is that rather than using I and j to refer to the indices that tell you which pixel you're on, we're now using coordinates x and y, continuous coordinates, and then the kernel offset parameters u and v have now been replaced with x prime and y prime. Additionally, I'm going to set the integration limits to positive and negative infinity because it makes the proofs a little bit easier. And to be honest, if the kernel is finite in extent anyway, then setting the integration limits to infinity doesn't really change anything. So it's just one of those algebraic conveniences that I'm going to take the liberty of using right now. Another liberty I've taken is with the representation of these two pictures at the bottom. So typically when you're building a convolutional network in, if you're writing the code, you need to worry about the color channels, R, G, and B. Now I'm not talking about actually using color channels in this context, but I have used color to denote these images at the bottom, especially that that continuous scalar field on the bottom right. So this is more of a talk about physics, I suppose, than it is about machine learning. So I'm taking the liberty of using orange and blue to denote the positive and negative values of that scalar field. But to be clear, they are single valued at each point. I'm not talking about three channeled color channels like you would normally need to worry about when coding a convolutional neural network. So I hope that's clear. And yeah, just like before, these are again spin zero fields, and when considering what the convolution is, it's now just a pointwise tensor product of two continuous spin zero fields. I say a tensor product because it will become clear later on why that's true, because when we're dealing with physical fields and kernels that involve different tensors of different ranks, in order to look at all possible couplings of those different ranks, we need to consider the tensor products. But in the trivial case where we just have a scalar image and a scalar kernel, then the two numbers just multiply together, and that's a very simple trivial case of a tensor product. But it's useful to think about it in terms of the physics language. So we have a spin zero field tensor product with another spin zero field, and that gives you another spin zero field as the output. In other words, scalar times scalar equals another scalar. Okay, so let's take a little step back and just look at the general setting of where we are. So we have our scalar field in the background behind me. It's constrained to the range 1 to -1. The kernel can scan the image, and the kernel offset vector is free to move within the kernel itself. I'm using the vector x, y to point to the center of the kernel, and the vector x prime, y prime to point to some point within the kernel. And under these circumstances, it's, like I said, easiest to use integration limits of plus and minus infinity, and we can now go ahead and prove that translational equivariance holds in the continuous case in a way that's frankly just as underwhelming as the discrete case. So let's go ahead and translate the image. We'll do g of v first and then do the convolution. That's achieved by just writing g of v in the integrand, and that of course just has the effect of subtracting a and b from the arguments, a bit like before. Now let's do the convolution first and then the translation. Well, now we're just going to subtract a and b from x and y correspondingly, and by virtue of the associativity of addition we'll just rewrite it and we can see that they are exactly the same. And that is the rather similarly underwhelming proof of translational equivariance in the continuous case. So in summary, we have our discrete convolution, the continuous convolution, and the proofs of translational equivariance in the discrete and continuous cases.